title today is half-life. Okay, so the half-life is the time required for a reactant to reach half its original concentration is called the half-life of the reactant. So again, the time required for a reactant to reach half its original concentration is called the half-life of the reactant. On your rate law table, it gives you formulas for calculating the half-life for zero order, first order, second order reactants. You can memorize those things if you'd like to, but my suggestion to you is to instead memorize the integrated rate law for that particular order of reactant, and then to find half-life, use the integrated rate law to do that. And we will do problems in class that show you, but I'll give you an example in a few minutes. But what is more important to me is that you understand zero, first and second order, what happens as concentration is decreasing. So you guys, let's first of all look at a zero order reactant. A zero order reactant. Okay, so we know that with a zero order reactant, it's the concentration versus time that is the linear relationship. And what this tells us, you guys, is that zero order reactants, when they get to half their concentration, let's say, here, okay, so here's this, so half our concentration, let's say, is right there. Okay, so it's whatever time it takes to get there. Okay, that's its half-life. And then we do that same amount of time again, reactant is gone. Okay, so that's it. It goes through a half-life, right? And then in one more half-life, it's over. There is no second half-life. It halves, and then in exactly that same amount of time, it goes to zero, and it's over. Okay, that is the case with a zero order reactant. It halves a certain amount of time, and then in that same amount of time again, that reactant is gone. It's been used up. That is not the case with first order and second order half-lives. Okay, so T1 half of first order. Okay, a constant time is required concentration by half. Okay, it is independent of the concentration. So what the heck do I mean by that? All right, well, if we've got a first order reactant, let's say that its concentration begins at, let's make this really easy for me, 5.00 molar. Okay, now, what is half of 5.00 molar? 2.5 molar. Okay, so let's say it takes 5 seconds for it to go from 5 molar to 2.5 molar. Okay, the next half-life, what is half of this concentration? 1.25 molar. Okay, it's going to take 5 seconds for it to go from 2.5 to 1.25. So this took 5 seconds. Okay, if it's a first order reactant, that one's going to take 5 seconds as well. Okay, what's half of 1.25? I didn't make it easy for myself. 0.625. That's not right. What is half? Okay, for this to cut in half again, you guys, the half-life is going to still be the same. It's going to take 5 seconds. Okay, so the half-life of a first-order reactant is the same. It is a constant time, 5 seconds, 5 seconds, 5 seconds, for the concentration to halve. Now, let's look at a second-order reactant. Okay, so T1 half of second order. By the way, T1 half means half-life. Okay, each successive half-life is double the preceding one. The preceding one. So it is, the half-life is dependent on the concentration. So if we use the same example here, right, we've got concentration and the amount of time it takes. Again, you guys, if we start at 5 molar and we half that thing, it's 2.5. And that takes 5 seconds. Half it again. How long is this half-life going to take? 10 seconds. To half it again. How long is this third one going to take? 20 seconds. Okay, so each half-life, each successive half-life is double the preceding one. So as the concentration decreases, it takes even longer for the concentration to cut in half again, to cut in half again, and to cut in half again. Okay, so we need to think about half-lives in this kind of way. And then the last thing I want to do, for instance, let's just, all right, let's use a second order reactant. Actually, let's use a 0. But again, I don't know, it's just so much stuff to memorize that the integrated rate law can be used for lots and lots of things. So let's write the integrated rate law for a zero order reactant and look at how we would figure out half-life from that. Okay, so the integrated rate law, so a regular rate law for zero order is rate equals K. Okay, so that's a zero order rate law. The integrated rate law is going to be the concentration of A is equal to, is it negative KT? Yeah. Negative KT plus concentration at time 0. A naught. Okay, so how are we going to use this to figure out half-life? We'd have to know the value of K, number one. In order to do it, in order to plug into the integrated rate law, we would have to know the value of K. But basically what we're going to do is we're going to take the initial concentration and plug it in, right? So plug in the initial concentration. Okay, you've got to know what K is. So you would have had to have solved for the rate constant already. Half of the initial, right? And we can do this for at first and second order as well. The initial concentration, half of the initial concentration, and then solve for T. And if you solve for T, then that is going to give you the time it takes for half of the initial concentration to